Magnetic propulsion utilizing Gauss's laws. Gauss's law states that magnets attract things from two ends, not just one. In this experiment, our Gauss gun was made up of several ball bearings, one strong magnet, and a ruler that we used as a track. When the magnet attracted one of the ball bearings, it would violently shoot another one off the end. Theoretically, momentum should be conserved in this experiment. We hypothesized that the change in velocity from the initial ball bearing to the other ball being shot off the other end of the Gauss gun would decrease with the number of balls that we attached to the Gauss gun before we launched one off. For this experiment, we did 3 different trials. For each trial, the end of the magnet was aligned with the 6-inch mark on the ruler, and the ball that was pushed toward the magnet was pushed from the 10-inch mark on the ruler. The first trial required a standard setup with 3 balls attached to one end of the magnet, and then the ball pushed towards the other end of the magnet. The second trial, we only had 2 balls attached to one end of the magnet, and then the other end, we shot the ball towards that. And then for the third trial, we again had 3 balls on one side of the magnet, but then we also added 1 ball attached to the other side of the magnet before we shot the second ball towards it. This is a visual representation of our 3 different trials performed in this experiment. These graphs represent the velocity of the ball that was launched off the end of the Gauss gun. For trial 1, the average velocity was negative 2.68 meters per second. For trial 2, the average velocity was 2.48 meters per second. And for the third trial, it was negative 0.59 meters per second. On the other end, these graphs show the velocity toward the ball that was launched towards the magnet in the first place. For trial 1, the average velocity was negative 0.165 meters per second. The second trial had a speed of negative 0.247 meters per second, and the third trial had a speed of negative 0.153 meters per second. As you can see, we did not very well standardize the speed that we launched the ball heading towards the magnet. For our first and third trials, they weren't very far off in speeds, but the second trial was much faster than either the first or the third. These charts show qualitatively what we would expect the kinetic energy versus potential energy graphs to look like for the first trial in this experiment. As you can see, the kinetic energy of the first ball heading towards the magnet is transferred into kinetic energy for the third ball on the end of the gun once it is launched off from the end of the gun. You can also see that the kinetic energy of the ball being launched off the end of the gun is actually higher than that of the original ball. This is due to the fact of the bonding energy of the magnet itself, which is very similar to what we'd expect to see in a chemical situation where bonds are attracting each other and when they break and reform. Also, you can see that once the ball is released from the end of the gun, that the first ball will have the same potential energy as the ball directly on the other end of the magnet. This is because even though they are on different sides of the magnet, they are still the same distance away from the magnet, meaning that they have the same strength of a bond attached to the magnet itself. Further analysis showed that the difference in velocity from our first trial and second trial were very similar, but for the third trial, the change in velocity was nowhere near as high. You can also see that the factor of increase from the initial velocity to the final velocity is very high in trial 1 and very low in trial 3, while trial 2 is closer to trial 1 than it is for trial 3. This is mainly due to the fact that for trial 3, there is balls both on the left and right side of the magnet before the gun is put into effect. As with any experiment, we did experience some errors. First of all, the slow frame rate of the recording software was not enough for us to be able to visibly see the ball very well as it was tracking, because the original video was very blurry because the ball just moves so fast on its own, so the tracking may not have been as accurate as we had wanted it to. Secondly, as we saw in our earlier results of the initial velocities of each of the balls, there was no standardized speed of launch towards the magnet for each trial. And lastly, each ball was tracked for a different amount of time, even though they traveled just about the same distance. Because the balls moved at different speeds, it took them different amounts of time to reach the end of the table, which was when we would stop tracking the movement of the ball. In conclusion, the difference in velocities from trial 1 to trial 2 was not very significant. However, comparing them to trial 3 did show quite a big change. That is because we did have balls placed on both the left and the right side of the magnet, causing the bonding energy to be separated into more places. The bonding energy on the right side was displaced through 1, 2, and 3 balls. However, the other side of the magnet put all of its energy into the first ball, which meant that not as much energy was transferred when the ball was launched towards the gun, meaning that the ball on the other side was launched up with a lower velocity.